Yeah, so I will be talking about charge transfer across a p-doped carbon nanotube using fabrication transition states using aniline. So as an introduction, carbon nanotubes can be readily used as semiconductors using P or N-type doping. And P-type doping describes incorporating a charge acceptor. N-type doping describes incorporating a charge donator. In the case of P-type doping, you can incorporate something like boron, or in N-type doping, you can incorporate something like antimony. Those are readily, donating charge or accepting charge, depending on which type of doping you're describing. For doping, it comes in many different concentrations. Particularly, there are 5 specific types of concentrations that are important for chemists who are interested in doping. It's plus, neutral, negative, and negative, which goes from highest to lowest concentration. And for my project, at least, we're looking at a P++ doped CNT, so a highly concentrated, charged, doped carbon nanotube. So for starting methods, just as sort of like a background for what sort of softwares I used, it was MATLAB, which of course was using evolution operator, basically evolving my wave packet as time went on. With VASP, I was using that to model the system that I'm talking about, which is going to be the transition state between aniline and a p-doped CNT. And using this specific model to calculate and generate the potential map, which is called lockpot for VASP at least, and then restricting that to the z-axis, so turning a 3D map into a 1D potential. And then once I have that potential, I can load it into MATLAB and use that as my wave packet to evolve. So just as a general set of equations, we have our evolution operator, of course. We have our wave function evolution, and we have our Hamiltonian in terms of momentum and mass, as well as potential. So the method that I used, at least, was to use the discrete matrix derivative and use it in the evolution operator. So essentially, I defined an initial wave function, which is my wave packet, which is the potential location map in 1 dimension over the z-axis, and defining the derivative as a Toeplitz matrix, and then using that in the momentum operator to change the Hamiltonian and evolution operators such that I can evolve them with respect to time, and then iterate for all the times that I want t. So this is just a general overview of the sort of coding that I did. So it was just basically taking this one, the initial psi naught in this case was just like a generic Gaussian wave packet, not necessarily my lockpots, which would just be load lockpots.z. Then I set my initial values and created the Toeplitz matrix that defines the derivative for the specific wave packet, and went up with the Hamiltonian along with the evolution operator, and then just looped it to create the simulation. So this was the beginning and final results. I'll show you the actual simulation here because I could not get it up on YouTube yet. All right. You can see the MATLAB, correct?
Yes. We see command line, and you need to visually show you, yes.
Yep. Okay. So this is the initial state. This is basically just a probability map of where the electron is, and the potential map will show up as well. So I'll press enter and just let it run. So we see that the sort of charge map here is gradually reflecting off of the potential well and creating this sort of centered area here. All right, super. So what we have, get back to this. All right, so this was our final result. Basically, what we're looking at is this electron is getting stuck in this potential well here, as you see with the many nodes here, but it's also allowed to still stay out of the node, considering the fact that the energy is still greater than the potential, and so then it can sort of split across the sort of potential that we're looking at. Let's see here, sorry. So clear electron probability above and below the p-doping site. So the x-axis in terms of angstroms and in Z. So the middle of this sort of potential well is where our p-doping site is, and we see this sort of weird horned function as our potential. And that's showing that there's a clear probability of this electron being in one of those two sites above and below the p-doping site. So that just sort of shows how, the aromaticity of a carbon nanotube, essentially, where the electron density is above and below the sheet. The electron density extends past doping site towards adduct, as well as throughout the CNT. This right side is showing the side that's actually going towards the adduct. And you still see like some amount of electron density over in that region because it is obviously trying to grab the hydrogen off of the CNT. Potential well shows structure above and below the doping site. So for further results, this is just showing the electron energy states. So we have the ground state, second state, yada, 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 on and on to n equals 15. And this is basically showing how different energy states react to this particular potential. With ground energy states, they're obviously stuck inside of that potential well where the potential is minimized. Whereas as you get further up, once you hit n is equal to 7, you end up with the electron actually going towards the higher part of the potential well because it's unimpeded by the actual well itself. The further and further you get from the proper energy levels, the higher tendency that these sort of electrons have to really ignore the potential well. So lower energy electrons get trapped, higher energy states are virtually unimpeded. Shows basically conduction band across the CNT surface because once you have an electron that goes down into that potential well, other electrons can't necessarily reach it unless they have higher energy states. And here are my resources. All right, any questions?
Okay, please join me in thanking August for interesting presentation and bringing us to the world of data imported from initial calculations. And before we start questions, I want to bring in an important correction with ambiguity of names. So let's fix an error right now online and then go to the questions. Let's slowly go to slides, forward. Copy the atomic image. Go to editing mode, maybe.
All right, sounds good. Give me a moment to exit out. All right.
Copy this image. Now go to the forward. Let's say this slide, yes. Paste it over here. And rotate by 90 degrees. And now expand a little bit so that it takes bigger. Yes, stop.
Okay.
Maybe move a little higher. So there was a little ambiguity in the namings, and I do not want anyone to, August and anyone in discussion to follow it. So P in your model was para orientation between adsorption site of this molecule and in respect to hydrogen. It's not P doping. It's para in chemical sense.
Oh, okay, gotcha. Yep.
What August was doing is to project this model along the axis onto potential. So middle is it's not because of doping. It is just because there is a grid of carbon atoms and contributions of atomic potential from all of them. From now on, let's open the discussion, and if anyone wants to please or challenge August with questions, please go ahead.